Hi, I'm Veronica Pinnick, and I am the Integration and Test Manager for PACE. And I went off of Gary's template when I made mine, so I have a little bit more about myself in the beginning parts of this, just to kind of give you a flavor of where I'm coming from. So I actually started out as a scientist. When I joined NASA, I did my PhD in analytical chemistry, and I built chemical sensors for chemically characterizing nanomaterials, like in a laboratory with giant benchtop equipment and huge vacuum chambers and things like that. And so when I graduated with my PhD, I was looking for a postdoc, and I saw a postdoctoral opportunity for building the same kinds of chemical sensors, except for looking at chemicals on Mars with NASA on a proposed mission for a rover to Mars. And so that basically got me in the door here, and from there I worked on a number of planetary science missions. And so I started out, as Gary was mentioning about the phases of NASA missions, I started out in phase E operations, looking at data that was coming down from MAVEN and from the Curiosity rover. And then I started up owning a piece of hardware, being a product development lead on a mass spectrometer that was going to Mars on the Rosalind Franklin rover, which is a European Space Agency rover that NASA contributed the main science instrument to. And there, on that mission, I was actually able to transition from working as a scientist and an instrument scientist, building the chemical sensors, to actually continuing up through the integration phase of becoming the integration and test manager to help organize the team and all the engineers and scientists to build up the suite and deliver it to the payload to the rover. And so after that, I realized, in fact, while I very much enjoy planetary science, Earth is one of the planets in the solar system. And so I came over to work on PACE on the spacecraft side of things. And so you have a lot of options as an integration manager, building things up at the instrument level. You can at the system level, you can either work on putting instruments together, the items that are actually looking at the science requirements, or you can build the even larger system of looking at observatories or different like rovers and things like that. So that's where I got into integration and test. And there are a lot of different roles that you can have, working at NASA. So I really like these different pictures, just kind of demonstrating all the different kinds of things that you can do, either as a scientist or as an engineer, whether that's working on a team like we have for PACE. I like that picture that Beth put up there, that we're really working with just loads of people underneath each scientific and engineering discipline. We're also able to put hands-on hardware and develop things that will fly to either different targets in our solar system or from Earth. And so here's a picture of me. This is the most recent one in the SCA, our spacecraft checkout clean room, which you guys will be able to see tomorrow, I believe it is the tour. And you'll see the PACE spacecraft being built there inside of that clean room. So, whoops, that's me. The little in case you couldn't find me. I know, I was like, we should play like can you find everybody from this tour in the picture? Okay, so again, borrowing Gary's slide about how all of our roles are kind of intertwined here on the team. So Gary and Eric both work on the systems team from the mission science level and the instrument science level. And so their goal is to basically define all of the requirements that we on the integration and test side then have to verify after the system is fully built up and we test it in its environments. And Beth's job is to, like she was mentioning throughout, is to get all of the spacecraft components delivered to the integration and tests, to my team, to get everything all integrated as a unit. And I was going to use my little box as a demonstrator here. So the first part of what I'm going to tell you about what integration and test, or I'll just shorten it up to INT. So what INT does is the first thing we have to do is build everything up. And so that's the build phase. And what I'll show you is that requires a whole bunch of different kinds of engineering disciplines. And depending on how you're putting things together, it's quite a complex complex process. You may think, I have 32. Is it 32 components? How many components on the spacecraft? 22.
22. But that doesn't mean like like we have like 4 reaction wheels. I didn't count that. Like 4 reaction wheels is 1. So
Yeah, yeah.
22 unique things.
Unique items.
Yes.
And so you might think, I'll put on box 1, then box 2, then box 3, then box 4, and then you'll have this flow, and you'll just have your teams all come in a row and just integrate these things. But what you find out, again, it all depends on the unique one-off mission that you have. You'll find that, well, box 1 had a problem in its environmental testing before it delivered to me, so now we need to plan the next thing. We can't call these doors because, as I was told, the reason why is because doors have frames, and the spacecraft, in fact, because of mass reasons, doesn't have a frame. So we can only open one panel at a time, and there are components on both the inside and outside of the spacecraft. So it becomes a bit of a dance where I need to integrate a component on the inside, but its harness goes across to the other side, and so I have to, basically work through a method of opening and closing and not, putting too much wear and tear on the flight units, and just make sure that we're continuing to close out as many of the items on the outside and on the inside and not lose too much time between, not being as efficient as we could be with all of the integration. So I like it because it's fun. It's like a puzzle, and it's always moving, and things are moving around. And my team is extremely good and flexible because they know that's what integration and test is. But it can give a lot of people heartburn. It can give a lot of people some stress, that's for sure. So after we build up the spacecraft, which I'll show you in just a minute, then we enter into the test phase. And these are the 2 main things I'm going to focus on just for today's talk. The test phase is not only after we integrate each one of these boxes or components on the inside or the outside of the system. After we integrate them, we have to test them functionally and make sure they are playing nicely with the other components that are integrated onto the spacecraft. But then, once we get receipt of the 2 polarimeters and OCI, and we integrate the full, what we call, it goes from a spacecraft, the vehicle, to instruments installed, now we're an observatory. Once those get all functionally tested together, then we go through what are called environmental tests, and I'll tell you about that in just a moment as well. And then, of course, INT also supports the launch phase, and getting the whole spacecraft and the observatory down to the launch site, all the activities that get you encapsulated and through the launch. So like I said, for the integration, it requires basically every discipline of engineering you can imagine. And so I only have pictures of some of the different disciplines. That even behind the scenes, each component, each box has its own team of people who do analyses, calculations, drawings, building hardware, actually putting these engineering units together, supporting us. So I'm responsible not just for building the flight units, but also for the, sorry about that, but also for building the flat sat, the flat satellite where we put together all the engineering units together to make sure that they play nicely together. So we have whole teams of people that support all of those activities. And so I'm just showing a few representations of some of the things that are happening. So we have, mechanical engineers who support integration and test by doing actually like the physically bolting on these components onto the spacecraft, torquing everything down, striping them with adhesives that keep them from moving or keep screws from backing out later on in the launch environments or in the testing of the launch environments, the environmental tests. They do all the analyses and things like that to make sure that physically everything is structurally sound. We have contamination and quality engineers. So Frank here, he's our actually quality, so I'll leave that for you to talk through in just a minute. But we also have folks whose job it is to make sure that we don't have chemical films contaminating optics or pieces of particulates. That's why we work inside of a clean room, just to keep all of our surfaces clean and to ensure that nothing migrates where it shouldn't be going for anything that's a mechanism or electronics box. We have to be super careful about stuff like that. So we have contamination engineers who keep our clean rooms intact, make sure we're doing the right things to keep ourselves off the spacecraft and vice versa. We have obviously electrical engineers. You saw some beautiful photos of harnessing from Beth, looking at the inside of the spacecraft, and from Eric, perfectly routed and managed, tied down harnessing electrical, components that you'll see. You'll see it on the smaller scale on some of these boards, and then on the larger scale on the flight units and the instruments in the spacecraft. So it's like a half art, half also, engineering feats. We have software engineers, so these are our colleagues from the Netherlands who delivered the specs instrument. And after the integration, they're basically looking at all of the software products that they put together to test the instrument, and then reading back all of those tests that they put together in these canned scripts, and reading back the data, making sure everything is looking healthy. We have thermal engineers who put together all of the blanket material that eventually go on the outside of the spacecraft to maintain its thermal environment in space. And we test those thoroughly in our thermal vac environment, which I believe we had a question about, so I'll hit that up in a minute. Optical engineers, I didn't have as nice fancy optics as Eric has pictures. I'm sure you guys have a whole suite of people, but depending on what your instrument is, that, in this particular case, we have a lot of optical instruments. And in other missions, you may have, very unique skill sets of engineers whose particular technique you need a lot of their analysis and also their hands-on skills to continue testing at the upper system levels. And then I really applaud Eric for what he said earlier about ground support equipment, both mechanical and electrical ground support equipment. Like he said, we build some of the most sophisticated science instruments around, and that also requires test equipment, which has to be equally as sophisticated, if not more sophisticated. And we have to almost tell our colleagues that I feel like maybe this room would understand. I feel like it's our engineering group at Goddard who sometimes don't fully appreciate the level of complexity that goes into the test equipment that also has to be used for testing these things, because we put so much effort into thinking about not having any kind of failures on the items that fly. We spend so much time thinking about the analyses and the engineering and all that stuff that goes into the flight units that go up. But the engineering material, or the ground support equipment that tests these hardware items, are just as important and just as complex a lot of the time. So a lot of folks in our group and our supporting groups design and build these electrical racks. And, oops, I think I have you can see for some of these items, the mechanical GSE can be just absolutely gigantic. And so in this case, this is our solar array gantry, and this is our structural verification unit of the spacecraft on the right. So not the flight unit, but basically our ETU spacecraft that checks the mechanical environments. And they're testing out the gantry and their fun little solar array wing here. So that is the mechanical GSE.
And those are weights that they put to spell go pace.
Yeah.
That's not what the real solar array will look like.
Yeah, I had that question a lot of times. Is that really, you're really gonna have that? I'm like, that would be cool, but no, those are just mass mock-ups. And so then, like I said, at each phase of integration of components, we also then have to do a full suite of testing. And so for that, it's not as easy to take photos of beautiful hardware and all the glamour shots that you get of the spaceflight hardware, but you also have very beautiful people who are in the room, all of us working together. It's between systems engineers. On my team, we have what are called test conductors, which are basically our software engineers who take the requirements from systems and then develop the software tests that do the orbits and the life. You basically try to do you simulate what an orbit would be like in performing all of those maneuvers that I think somebody was asking about all the different kinds of maneuvers that you have to do. So we test all that stuff out. The more we build up the spacecraft and the more we include the instruments in that suite, the better our tests get and the more flight-like they get. So we just do it baby step it up, just little by little, test out the functionality as we include different components onto the spacecraft. And so right now we have a good number of the components on the spacecraft. You said 22, so where are we at? I think we're at 18? 18 components, so we're getting very, very close, and we're very much looking forward to our deliverables of our flight instruments later this year. So after we get through that very challenging portion of spacecraft integration where everything, there's kind of a lot of parallel paths, you can kind of put on different components, you can open up the panels a bunch of different ways and put on the components at a bunch of different kind of in a different order. we start to enter a single phase, which is, now we have all the spacecraft components integrated, we have the instruments integrated, we've tested everything as much as we can to perform what like a baseline or a pre-environmental, test profile. Then we head into the portion of the tests which are called environmental tests. And so this is something that for me was very new coming to NASA from the laboratory and from the university, where, I had built lots of instrumentation, for different reasons. And usually you have all the resources in the world. You have the entire, okay, it's university, so you don't have maybe all the money in the world, but you have a little bit of space, you have the ability to buy things off the shelf. You can put things together and you can kind of be a jack of all trades and kind of make it work. If it doesn't work the first time, that's not the end of the world. You just keep working on it. Here with spaceflight, you're usually constrained on a number of those things. So I guess that's the M and M that Gary referred to. But you also have to ensure that your instruments are going to survive your very precious, very expensive scientific instruments that you spent all this time developing, from the proposal phase through design and build and calibration. You have to make sure that they're going to actually survive the launch and getting out to where they need to go. So we do these tests that are called environmental tests that check a number of different components that get you through basically testing as you're going to fly. So they say test as you fly and fly as you test. So the goal of environmental testing is just to make sure that all that time that you spent was not for naught, and that it's going to survive once it actually gets to space. So the tests themselves verify a number of things. There's sometimes that you do a lot of analyses to prove that something should work. You do a bunch of calculations and you say, okay, if I have these set points of temperature, then my unit should only ever see this temperature. Or if I build my component on this, aluminum structure with these, physical features, when it vibrates as it goes up in the launch vehicles, it should never see more than this deflection angle or something like that. You do all these calculations. So these tests actually prove out what you think is going to happen. It really does happen as it's built. And we do these tests sometimes, if you have enough money and you have enough time in your schedule, at the engineering unit or with units that aren't the flight ones. You don't do these right away, like directly on your flight unit, because if you're wrong, if you find out you're wrong, that's a bad time to find out is on your flight unit, right? So that's why we have these engineering units, or even smaller structural verification units or other, earlier phase, maybe a lower fidelity items that you can test ahead of time to kind of ring out those problems that you might have. But those prove out your analyses. And then, because each of these spacecrafts and each of these instruments are truly usually one-offs, we're not really in the business of production line development. Because these are one-offs, there's this thing called workmanship, which is really just testing each person's hand-to-hand building something. How did it all work? And is it reproducible? And can it survive the environments that it's going to see for launch? And then finally, things like performance and calibration in its realistic environments. That's kind of what thermal vacuum is for. So really testing some of the things that you have on your instrumentation can't be proven anywhere else but in the thermal vac or in the environmental test, because it's not meant to fly. It's what is Wendy's
You can't
phrase?
fly a spacecraft in a room.
Which means
You can't fly a spacecraft in a room. But actually, you can, but it's really expensive. You just want it.
right. So you don't want to design your spacecraft to work on Earth, on the ground. You want it to eventually work there. So some of the tests you can't prove out till you're at the environmental testing. So the three environments I'm going to kind of tell you about today is EMI, EMC, electromagnetic interference and compatibility testing. I'm going to tell you about mechanical environments, and then I'll tell you about thermal vac. So we'll start with EMI. So I don't even know if this analogy works anymore with technology that we have now, right? Because nobody has these TVs that actually maybe see this kind of interference. But I think, so the idea is to make sure that nothing on your spacecraft, none of the electrical signals and the noise that exists on your spacecraft interferes with your science instruments or your spacecraft components, that you yourself are compatible and all the instruments and the components play nice with one another, but you're also not susceptible from the launch vehicle or from anything that might radiate out in space to interfere with you. So we do all of these testing, and we go into these chambers that are, kind of cut off from all electromagnetic interference. That means no cell phones. You have to, kind of keep everything very chill in there. So this is a picture of OCI. I think this just happened. And this is one of my previous projects in a smaller room. And so you look for things conducted. That's kind of that line that's going between that person drilling on the same surface as that television, creating noise that you see conducted through the power lines themselves or on your data lines themselves. Or another option is to check radiated emissions. So as we're communicating through our antennas, just making sure that doesn't interfere with anything that OCI might be looking at on one of its detectors. So we look at both radiated and conducted susceptibilities and characterize our own emissions on our spacecraft as well. So the next environment is maybe a little more straightforward to kind of think about is, when our spacecraft is encapsulated and it's on its launch vehicle, it will shake. when we send it up into space, it will go through physical vibrations, and so we try to test that as much as we can and isolate those as much as we can by putting them on shaker tables, and also using sound waves basically to simulate the different frequencies and intensities that our spacecraft could potentially see in its launch environments. So we go through a pretty good amount of back and forth with our launch vehicle providers to kind of talk through what the full, worst case scenarios of our levels could be. And we go and test both at our lower levels, again, at the box level and at the instrument level before it gets up to the spacecraft and observatory level. And then we do it again once for the whole built up units. We check both the 3-axis vibration, acoustics, and shock, which is exactly what it sounds like, and checking to make sure that any mechanisms that you have that fire, that induce a shock load, how it propagates through your system, make sure that you're not damaging your own self when you actuate some of these components, and making sure that your launch vehicle doesn't induce those shock loads onto your spacecraft. So we go through all of these, and I think we'll show you all of these when we walk through the facilities tomorrow. So yeah, I think usually that's what people see when they come to the complex, is all of these different facilities where you can do these kinds of environmental tests. So we'll take a look at some of these things. And so the last one is the big one. That is our thermal vacuum testing. And so this one these are big, giant vacuum chambers that the goal is you're trying to simulate whatever environment you're going on. So earth science oftentimes is actual vacuum. If you're trying to simulate some of the planetary science missions, sometimes you have to simulate more complex environments, like Mars would be mostly CO2. If you're going to Venus, it's high pressure. So there's some unique things depending on your planetary target. But Earth, you go into these chambers and they pump out the air and create a vacuum. And then we just check basically all of our thermal modeling. So, we can do contamination bakeouts in a vacuum, so we can kind of remove all of the excess water and hydrocarbon contaminations. And we can then go cold and bring the entire chamber to hot and cold environments to simulate the cycles that it'll see, going from hot and cold orbiting the Earth. As well as just trying to do some work, like checking out some workmanship things. So usually what they say is that when you go through your environments, you go EMI, mechanical environments, and then thermal vacuum. Because in mechanical environments, you shake things like solder joints and things like that have workmanship in that way for electronics. And then if anything got weakened in that vibration test, that's usually where it breaks, is the thermal cycling of those components. So, yes? The thermal vac profile, do you know off the top of your head what are?
Each component is different.
So the
Well,
space
let's say-
environment is very, very hot and very, very cold. And then the thermal engineers do an awesome job of saying, this device or component, what do you need to work well? So detectors like to be cold. Minus 85 degrees C to minus 40 degrees C are the OCI detectors. But then some of the electronics want to be 0 degrees C. And some things like to work warm, like our bearings on our mechanism. So they want to be like 20 degrees C. So there's a whole range, and so we'll define like an operational range where we know they're going to meet the performance, then a survival range, and then a thermal system has to wrap all that up and control everything from the very, very cold to very, very hot environment to make sure everything's balanced and working well.
Yeah, and based off of that, some of that analysis, then those thermal engineers recommend heaters in certain locations, survival heaters that never let something get below a certain temperature, blankets in some areas, radiators in some areas. And so that's kind of how they design it. And this is the test that basically proves out, if I give them the bulk temperature of this temperature, based on your modeling, what should your values be? And then you just correlate it that way. And were you going to say something else, Beth?
Oh, just that they ended up putting additional plates or panels to help also control, rather than the heaters themselves are allowing them fly or part of the spacecraft, but they'll actually put out additional panels within the chamber to also control temperature.
That's right. That's right. Yes. Let's see. Yeah, I think I hit all of those items. And so this is the SES chamber, which again is a pretty impressive site. It's hard to, I don't know if there's people that really show you how large this thing is, but you will see it as part of your tour. And it's very impressive because it's multiple stories, and you think you've seen the whole thing, and it actually goes down further into the floor as well, where all the pumps live and things like that. So it's a very impressive facility, and it doesn't just service NASA missions, but also has outside vendors also coming in and using the facilities as well. So after we get through the system level test, thermal vac is our last big test before we put our solar array on, just check that everything is functional one more time, pack it up, and then we ship it to the launch site, and then you get that fancy video, which I still have yet to actually launch a mission, so I'm very excited that I hope that base will be my first one. We'll support all the way through the activities of getting it encapsulated, getting it out to the pad, launch, and we'll support about the commissioning phase, which is 60 days post-launch. And just for fun, I have a silly little video, but that is what I have, and I'll take any other questions that you might have about environmental testing or integration and test.
This is a little bit of a silly question, but do these,
That's not what it does.
does it get driven on a truck? Does any satellite that gets launched get driven on a truck, or do sometimes you have like the Air Force fly it or something?
There are lots of options. I'll say JW had to go on a boat. We will drive on a truck. It's fancier than probably what you're thinking. We don't just throw it in the back of a FedEx truck.
There's a box.
But yeah. So we have a shipping container that supports it, in a sideways configuration. But it's also air padded and temperature, humidity controlled. It's on a constant purge line. And I believe there's a car that drives behind that kind of keeps eyes on it at all times. And if ever there's a need, one of the temperature, humidity, or purge, or any of those alarms goes off that indicates there might be an issue, you have a team of people who can respond and deal with it. But we're driving from here to Kennedy, so not too bad. Not too bad of a drive. Other questions?
How does the satellite keep the balance in the space? So, because I sometimes see some satellites have two wings and sometimes has one wing. And how do they maintain the balance on the orbit?
So I think the number of solar panels depends on the energy needed by the system.
No,
Are
your
you talking
orbit.
about thermal balance or
Which?
orientation?
Yeah, orientation.
So the thing that's going to move it out of position is drag from the atmosphere. As you get further and further away, there's less drag. So there may be some drag, but at the end of the day, you're in space and you're free falling, so it is what it is. So in low Earth, they use a reaction wheel. Just a big momentum wheel, big disc that you spin up and spin down, and if you've ever done the basic physics experiment, spinning a bike tire and turning it, you spin about your chair. Same idea. So the guidance, navigation, and control engineers figure out how to orient four, 5, 6, whatever the right number of these wheels in different orientations, and they'll spin up different combinations of it to move that torque vector around. And so I need to look here, and so they'll spin up the right wheels, and it will make the satellite point and lock onto a target and hold it over time.
We have 4 on the inside.
Do you need manpowers to do?
You need what?
Do you need manpowers to monitor it, or it's like automatic?
sensor data from gyroscopes around the sensor, as well as like the core sun sensors that Gary said. There's a whole number of sensors that will feed information to the computer, and it makes a decision on what needs to happen to maintain the pointing.
Yeah, and they have gross control, like you were saying, with the reaction wheel, momentum. There's fine control from electromagnets that are basically spun and are turned on to the, there's 3 of them for each axis that you can then do fine motor control and things like that. And there's thrusters as well for navigation as well.
And your question is a good one. In addition to drag from the atmosphere, some missions that go very far away from Earth, if they want to stay pointed accurately for a long time, if they only have one array, there's solar radiation pressure that will push the spacecraft in a different attitude. And so sometimes they'll have a boom on the other side with an equivalent area just to keep themselves balanced. Or sometimes they'll have trim tabs that can adjust the amount of area that's seen so they can balance out.
But the reason why,
It's a good question.
the reason why we have one solar array is we're sun synchronous. So basically the same side of the spacecraft always sees the sun. So the other side would never see the sun, so there's no point of having a solar array. So it does depend on your orbit too, how many solar arrays you have.
Thank you.
Any other questions? Okay. Yeah, thank you.